Level 0. The moon takes a chunk out of the sun, and suddenly your Monday afternoon feels like the opening scene of an apocalypse movie. This is a partial solar eclipse, the most common type. But what's happening is a cosmic alignment so precise it shouldn't be possible. The moon is 400 times smaller than the sun. The sun is 400 times farther from Earth. This perfect ratio means they appear almost exactly the same size in the sky. No other planet in our solar system has this setup. Not one. During a partial eclipse, the moon slides between Earth and the sun, but the alignment isn't quite perfect. It's like trying to cover a spotlight with a dinner plate while standing slightly off to the side. Part of the sun remains visible, a blazing crescent that still pumps out enough light to cook your retinas if you stare at it. This is why you need eclipse glasses, the ones that make you look like a time traveler from a budget sci-fi film. The partial phase can last hours, depending on your location. The light gets dimmer, taking on a strange silvery quality that makes everything look like it's been dipped in mercury. Shadows sharpen, colors mute. The temperature might drop a few degrees. Birds get confused and start their evening routines early, singing sunset songs in the middle of the afternoon. But millions experience partial eclipses and don't even notice. The sun is so bright that even 50% covered, there's still enough light flooding the sky that life continues as normal. You could be having lunch, scrolling through your phone, completely unaware the moon is performing celestial photobombing above you. Ancient civilizations noticed, every single time. Imagine being a farmer in Babylon, watching the sun devoured by an invisible force. No warning, no explanation. They thought it was divine punishment, a dragon eating the sun, the gods expressing displeasure. When your entire understanding of the universe depends on the sun rising and setting like clockwork, any deviation is an existential crisis. The partial eclipse is your tutorial level. The universe shows you the basic mechanics before it really starts showing off. Because what happens when the moon doesn't just take a bite out of the sun, but swallows it whole? Level 1. The moon passes directly in front of the sun, and instead of darkness, you get a perfect golden ring blazing in the sky. This is an annular eclipse, from the Latin annulus, meaning ring. It's what happens when the cosmic geometry is perfect, but timing is slightly off. The moon's orbit isn't a perfect circle, it's an ellipse. Sometimes the moon is closer to us, about 225,000 miles away at its nearest point, called perigee. Sometimes farther, about 252,000 miles at apogee. This 27,000-mile difference might not sound like much on a cosmic scale, but it changes everything. During an annular eclipse, the moon is farther from Earth, appearing slightly smaller in the sky. When it passes between Earth and the sun, it's not quite big enough to cover the entire solar disk. The result is a ring of sunlight, a perfect halo of fire surrounding the moon's silhouette. It's breathtaking. It's also still dangerous because that ring is the surface of a star, still blasting out enough radiation to damage your eyes permanently. The ring of fire might sound romantic, but it's still a thermonuclear furnace. The annular eclipse creates one of the strangest lighting conditions you can experience on Earth. It's not quite day, not quite twilight, but something in between. The light is dim enough that streetlights might flicker on, but bright enough that you can still see colors clearly. It's like someone put a cosmic dimmer switch on reality and turned it down to 60%. The path of annularity, the narrow track on Earth's surface where you can see the perfect ring, is typically only about 100 miles wide. Step outside that zone, you're back to seeing a partial eclipse. This makes annular eclipses a traveling show. People chase them, booking flights and hotels years in advance, all for a few minutes of standing in the shadow of a ring. But here's what haunts me. They're a preview of the future. The moon drifts away from Earth at 1.5 inches per year. It's caused by tidal forces, the same forces that create ocean tides. Over millions of years, this adds up. Eventually, it'll be too far to ever create a total solar eclipse again. Every eclipse will be annular. That perfect 4:0:1 ratio? Temporary. We're living in a narrow slice of cosmic history where total solar eclipses are even possible. So, what happens when the moon is at the right distance and the alignment is absolutely perfect? What happens when the moon doesn't leave a ring but instead swallows the sun completely, plunging the day into night? Level 2. The world ends, and then 2 minutes later, it comes back. A total solar eclipse is the most spectacular natural phenomenon you can witness from Earth's surface. Nothing compares to standing in the path of totality and watching the moon completely obscure the sun. First comes the partial phase, lasting over an hour. The moon slowly eats into the sun, a dark semicircle taking increasingly larger bites. The temperature drops, the light becomes metallic and wrong. Animals start acting weird, birds going silent, crickets chirping, thinking night is approaching. Then, minutes before totality, things get really strange. Shadow bands appear, wavy lines of shadow rippling across light-colored surfaces like the bottom of a swimming pool. These are caused by the sun being reduced to a thin crescent, which makes the light more directional. allowing atmospheric turbulence to create visible patterns. And then Bailey's beads. In the final seconds before totality, the last bits of sunlight shine through the valleys and mountains on the moon's edge, creating brilliant points of light that look like beads on a string. This lasts only seconds, a cosmic farewell before the main event. And then, totality. The moon covers the sun completely, and the sky goes dark. Not sunset dark, but wrong dark. The kind of dark that triggers something primal in your brain. Stars become visible, planets appear. The horizon glows with a 360-degree sunset effect. And around the black circle of the moon, the corona appears. The sun's corona is its outer atmosphere, a halo of superheated plasma extending millions of miles into space. It's always there, but normally it's invisible because the sun's surface, the photosphere, is a million times brighter. During totality, with the photosphere blocked, the corona reveals itself, a ghostly white crown of light streaming out in all directions, following the sun's magnetic field lines. The moon moves at about 2,100 miles per hour relative to Earth's surface, so totality doesn't last long, anywhere from a few seconds to about 7.5 minutes, depending on location and geometry. The longest possible duration for a total solar eclipse is 7 minutes and 32 seconds, and that's under absolutely perfect conditions that rarely align. When totality ends, it ends suddenly. The first ray of sunlight breaks around the moon's edge, creating the diamond ring effect, a brilliant point of light that signals the end of the show. You have to look away immediately, because that single point of sunlight is enough to damage your eyes. The spell is broken. The world floods with light again. Total eclipses are rare for any given location. On average, any specific spot on Earth will experience a total solar eclipse once every 375 years. You could live your entire life in one place and never see one. This is why eclipse chasers exist, people who travel the globe following the shadow, racking up totalities like stamps in a passport. But what if the eclipse can't make up its mind? What if it gives you both annular and total, switching between them as it crosses the planet? Level 3. Sometimes the universe can't decide, so it gives you both. A hybrid eclipse is the rarest type of solar eclipse, accounting for less than 5% of all eclipses. It's what happens when the curvature of the Earth and the moon's distance create a situation where the eclipse appears annular at some points along its path and total at others. During a hybrid eclipse, the moon is at a distance where it's just barely big enough to create totality. At the beginning of the eclipse path, when the moon's shadow first touches Earth, it might hit at a point where the curvature means the moon appears slightly smaller, creating an annular eclipse. As the shadow moves to parts more directly beneath the moon, it appears larger, and the eclipse becomes total. Then it might switch back. The hybrid eclipse of the 20th of April 2023 started as an annular eclipse, transitioned to total as it crossed parts of Indonesia and East Timor, then switched back briefly before ending. The path of totality was narrow, barely 30 miles wide in some places. Standing in the path of a hybrid eclipse is surreal because you're acutely aware of how fragile the geometry is. A few miles in any direction, and the show would be completely different. Hybrid eclipses are so rare that most people, even eclipse enthusiasts, will never see one. The next hybrid eclipse visible from Earth won't occur until the 14th of November 2031. After that, April 2043. They're that rare. But what happens when the eclipse doesn't happen on Earth at all? What happens when the shadow falls on another world entirely? Level 4. Jupiter's moon Io crosses in front of the sun, and its shadow races across Jupiter's cloud tops at 38,000 miles per hour. Solar eclipses aren't unique to Earth. Any moon can create an eclipse on its planet. The solar system is full of shadows, and some of them are far stranger than anything we experience here. Jupiter has 95 known moons, and the 4 largest regularly cast shadows on the planet. Because Jupiter is farther from the sun, these shadows appear as perfect black circles racing across the planet's turbulent atmosphere. Io orbits Jupiter once every 42 hours, and its shadow moves at incredible speeds. Mars has 2 tiny moons, Phobos and Deimos. Phobos is only 14 miles across, so when it passes in front of the sun, it appears as a dark potato-shaped blob that doesn't cover the solar disk. It's more like watching a flying saucer drift across the sun. The Curiosity and Perseverance rovers have photographed these transits multiple times, but Phobos won't be creating eclipses forever. It's slowly spiraling inward toward Mars. In about 50 million years, Phobos will either crash into the Martian surface or be torn apart by tidal forces, creating a temporary ring system around Mars. The eclipses we see on Mars today are temporary. And then there's the most extreme eclipse scenario in the solar system. Standing on one of Saturn's moons during an equinox, twice during Saturn's 29-year orbit, the rings align edge-on to the sun and cast a massive shadow across Saturn's equator. If you pass through this shadow, you'd experience an eclipse created not by another moon, but by billions of chunks of ice orbiting the planet in a disk. The universe has taken the basic concept of one object blocking light from another and created infinite variations across countless worlds, each one revealing something different about orbital mechanics and the interplay of light and shadow. But what about the eclipses that we've never seen? The ones that happened before humans existed, or will happen long after we're gone? Level 5. On the 7th of August 1869, a total solar eclipse crossed North America, and astronomers used it to prove that helium existed. During totality, they analyzed the light from the sun's corona using spectroscopy. They found a yellow spectral line that didn't match any known element on Earth. They called it helium, from Helios, the Greek god of the sun. It would be another 26 years before helium was discovered on Earth. Eclipses aren't just beautiful, they're scientifically revolutionary. They've allowed us to study the sun's corona, test Einstein's theory of general relativity, and reveal the existence of the chromosphere. The total solar eclipse of the 29th of May 1919 is the most famous eclipse in scientific history. Arthur Eddington photographed stars near the sun during totality to test Einstein's prediction that the sun's gravity would bend starlight. Eddington's photograph showed the stars shifted by the exact amount Einstein predicted. One eclipse changed physics forever. But we almost didn't get those measurements. Principe was cloudy that day, and Eddington was photographing blind. The clouds parted for just a few minutes, barely enough time to capture the data. Looking forward, on the 12th of August 2045, a total solar eclipse will cross the United States coast to coast, with totality lasting over 6 minutes in some locations. People are already planning for it decades in advance, but there are also eclipses we'll never see again. The last total solar eclipse visible from London was on the 29th of June 1927. The next one won't happen until the 23rd of September 2090. The last total eclipse visible from New York City was on the 24th of January 1925. The next one is on the 1st of May 2079. Every eclipse is both a repeat and a unique event. The Saros cycle, about 18 years, 11 days, and 8 hours, causes eclipses to repeat in similar patterns. But they don't repeat in the same locations. Each eclipse in a series shifts westward by about 120 degrees longitude. Eventually, every eclipse series ends, the geometry drifts out of alignment over centuries, and the shadows stop falling on Earth altogether. And here's the most existential question. What happens when the moon itself can no longer create total eclipses at all? What happens when the moon drifts so far away that every eclipse becomes annular, and the era of totality ends forever? That's not a question of if, it's a question of when. And the answer is both fascinating and melancholic. Approximately 600 million years from now, the moon will drift far enough from Earth that total solar eclipses become impossible. The moon is leaving us. It's been leaving us since it formed 4.5 billion years ago, and it'll keep leaving until either the sun expands into a red giant and swallows both Earth and moon, or until the moon reaches a stable distance about 43% farther away than it is now. Right now, the moon recedes at about 1.5 inches per year. That's roughly the rate your fingernails grow. It doesn't sound like much, barely noticeable on human timescales, but over deep time, it compounds. Every year, the moon gets a tiny bit smaller in the sky. Every year, total eclipses become a tiny bit rarer, their paths narrower, their durations shorter. In about 600 million years, give or take 100 million, the moon will be too far away to ever cover the sun completely again. Every eclipse after that will be annular at best, a ring of fire but never totality, never the corona, never that moment of primal darkness in the middle of the day. The era of totality will be over, and it will never come back. This means we're living in a special time. Not just humanity, but all life currently on Earth exists during a narrow window of cosmic history when our planet happens to have a moon that happens to be at exactly the right distance to create perfect, total solar eclipses. Dinosaurs saw them, watching the sky go dark 100 million years ago, probably confused and frightened. Early mammals saw them. Ancient humans saw them and thought the world was ending, creating myths and legends to explain the impossible sight of the sun being devoured. But nothing that comes after us, assuming life survives the next 600 million years of evolution and environmental change, will see the corona emerge from behind the moon during totality. They'll read about it in whatever passes for historical records in that distant future. They'll see videos and photographs, assuming any of our data survives that long. But they'll never stand in the shadow and feel that primal wrongness of the sun disappearing in the middle of the day. They'll never experience what we take for granted. The universe has given us this gift, this perfect alignment of sizes and distances, and it's temporary. We didn't do anything to deserve it. We didn't earn it through effort or virtue. We just happened to evolve during the right epoch, in the narrow window between the moon being too close and too far away, when total solar eclipses are possible. And here's the really unsettling part. The moon's recession rate hasn't been constant throughout Earth's history. It's been faster in the past, slower at times, influenced by the configuration of Earth's continents and oceans, which affects how tidal forces transfer energy between the Earth and moon. Some scientists think the moon might have been creating total eclipses for only the last few 100 million years, which would mean it's been possible for perhaps a quarter to a third of Earth's history, and it'll stop in the next few 100 million years. That makes the window even narrower than we thought. We're living in the eclipse window, a brief, bright moment in the 10 billion-year lifespan of our planet, when the sky can go dark at noon, when the sun's hidden atmosphere becomes visible, when the universe reminds us that even the most reliable constant in our lives, the sun itself, can be obscured by something as simple as a rock orbiting our planet. It's a reminder of how precarious and precious our place in the cosmos really is, how much of what we experience depends on accidents of timing and distance that we played no role in creating and have no power to preserve.